1 divided by and put a bracket in. The reason for that is because if you don't do that and you put it in as 1 divided by 2 times by pi, it will start off by doing 1 divided by 2, which is mathematically incorrect for this formula. Okay? So you can see, I've pressed the fraction button, I've put 1 at the top. This centerpiece here, I've hit the down button to get me down to the bottom. So I can now start to put in 2 times by my pi times by my 100 hertz, okay, and times by 10. And I've stopped there to make sure that you spot this next step. To put the power of into your calculator will have one of 2 buttons. It'll either say EXP or it'll have X10X.
X10X? Times 10 times 10 or?
It's times 10, because it's 10 microfarads, to the power of 10 to the power of minus 6. So this power of 10 to the minus 6, you either have this function button just here that says X10X or EXP on your calculator. Okay? So you hit that button, and then you can put minus 6. Okay? If it was a positive number, you could just put 6 in. Okay, but this is minus 6. Okay, and then hit equals, and you should get 159.1559 ohms.
1549431.
That's that. Yeah.
No, I've got, yeah. I think my calculator's the same. Yeah.
EXP. Mine's got EXP.
Get a highlighter and you highlight 100 volts. You highlight 100 ohms.
You're not recording?
Audio only.
Or is it audio today?
Audio, yeah.
Alright, so you're experimenting.
Yeah, I suppose I am, yeah.
Actually, the class was asking if we all can get a copy of your recording.
Well, it's a good idea, and I'm here all the time. I'm recording as much as I can.
Yeah.
Yeah. I don't know how to do it. Do you know what? I don't even know how to get it out of my Apple phone and put it into my Microsoft laptop. I've been trying to do it and I've been struggling. But I'll look at it again. Yeah. But once I get it into my laptop, I don't know, what do I want to do? Email it to you? In the past, have you heard of Dropbox?
I'll put it on a USB.
You want USB? Okay. Have you heard of Dropbox?
Yeah.
Maybe.
Yeah, can use Dropbox.
Yeah.
Yeah. WhatsApp as well. No, WhatsApp too heavy. Too heavy. 1 hour is too heavy. But Dropbox will work. You can put movies on Dropbox.
Yeah. When I get home, I laminate these.
Is that what you do?
Yeah, because I imagine myself one day to be in a van talking to someone else, whether it be me learning or whether it be me teaching. So I thought I'd laminate them because in the past I've lost them and stuff.
That's very good. Why don't you just download all of them off?
I will do.
Because that's what I did from last year. Not all of them, but whatever I needed, I just laminate. I just downloaded it. But Heather was very good at that, wasn't she?
She was, yeah.
I've got a question. Where does so it says 100 volts? Yeah. So I know it's going through a transformer, but it says 100 hertz. How do they change the hertz? You know? I don't know.
No, what
Sometimes you
what
have it
increases
for
the
voltage or something like that. You have like inverters,
Yeah.
and over there you can change the frequency. It's the only one thing which I saw it where you can change the frequency.
Inverter, yeah.
That's more electronics than engineering, isn't it?
Because I work in instrument engineering and food factory, yeah, you have all the kind of bells for transporting the bread, yeah. So you see there, you need more than just barely move, you know.
Yeah.
And they have like inverters and they set up them, you know, like as people need. That is the only thing what I saw with actual on this one.
Right, everyone with me so far, what we've done?
Yeah.
James.
Okay. Right.
Just call him. I wasn't here for 10 minutes. James, just the thing, because I wasn't here for the first 10 minutes. When you say you're looking for impedance, you're looking for Z, you're not looking for the XL.
So we've got to work out the XL and the XC first before we can get Z.
Yeah, when it says look for impedance, that's Z.
Yeah.
Oh, okay.
Z is impedance,
Yeah,
isn't it?
I was just been here for 10 minutes, so I missed out.
Okay.
Right, so now we've done the first bit. That's the bit that changes. Okay. So we've been given a constant resistance of 100 ohms, haven't we?
Yeah.
Okay. So our 100 ohms is what goes on the bottom here, because it's the resistance. Okay. So we can now go back to that Pythagoras theorem of adding it all together, can't we?
Yeah.
To be able to get Z. So I'm going to be doing 100 squared plus 159.15 squared, square rooting the whole formula to get my Z. Okay, have a go at that, please, gents.
Do you do that with an open bracket? Do you do that in brackets?
Yeah.
Depending on the type of calculator you've got, some of them do need you to put a
So
bracket.
mine's similar to the one that you've got on the board.
You don't need to with my one.
Right. So square root symbol first.
If you've got an old scientific calculator, you will need to put it in brackets. If it's a modern one like the one on there, you don't need to. It will automatically send it.
Because everything.
It is best practice to put it in brackets to make sure.
No, you don't need to put another square root.
Let's try that.
Have you done it in your head, have you?
Square root.
Just put the numbers now. Don't put another square root because this one will be for whole lot.
That's only because it's written on the paper in front of you.
No, you need to be
James.
100
So
square.
So square root symbol.
Square root symbol.
Yeah. 100.
Squared.
Yeah.
You need to square that 100.
Ah, that's the x2 in it.
Yeah.
Plus.
Plus.
Square root symbol again?
No.
Okay. 159.
159.
That's what I was doing.
And then square that number.
Yeah, but the problem is now you have it 2 square roots. You see?
Yeah, but that's what you're asking, the square.
No. You have 2 square roots.
Okay, one square. Right, so 159 square root. Yeah? Yeah?
100.
Yeah?
Square roots.
Yeah?
It's equal. That's it.
Yeah.
What do I do for them?
No, you press it 2 times the square root.
Ah, I've done 2 square roots rather than 2.
Yeah.
I see. Let's try that again. Yeah, I know what I've done.
So, is it 187 that you've got for this? Perfect.
I know what I've done.
So that is our impedance, 187 ohms for this circuit. Okay? The next thing we've got to do is work out the current. How do we work out the current again?
Voltage divided by impedance.
Voltage divided by impedance.
I got the wrong thing. Yeah.
Okay? So 100 volts divided by 187 ohms
0.53.
equals
0.534.
so 0.53 amps. Have you all managed to get that?
Yeah.
Perfect. Okay. Are you all happy so far?
Ecstatic. Do you know, I normally do this stuff over the weekend, but this last weekend I was so fucked. Well, I sat down Sunday, thought, right, I'm going to sit down and look at this. Got it out. I think my daughter called me to go and look at something. Went and looked at something, sat down, put it away, thought, fuck, I'm fucking wrong with it. I'm going to try and do the one from last week and this week's one this weekend. So I think if you do it, if you have a break for a couple of days and you do it, it sort of keeps it fresh. Whereas now I'm sitting here thinking, it all sort of comes back to me, but it doesn't. It's not sitting there like fucking fluctuating to.
That's why I tend to use my own writing. That's why I tend to write. So, I've skipped the next two slides because it's what I've already been explaining to you about with the fact of how it's all laid out already. Okay? The only thing I haven't drawn on mine is the PF, the power factor that sits in the middle. Okay? So, this really complicated looking diagram here. Okay? We need to start off by looking at it and ignoring a few bits first of all. Okay? If we are to look at it with resistance and our XL being here first of all, okay, that's our inductive load having a really large resistance. Okay? Who remembers the word that I used last week to try and remember which one had a leading and which one had a lagging power factor?
Civil.
Civil. Okay? So the inductor has a lagging power factor, which means it's got a really large resistance. Okay, does that make sense so far? Okay, so if I was to put in this capacitor, okay, which has a lagging, which is why it's down at the bottom, has a leading, which is why we put it down at the bottom, okay, has an opposite power effect, doesn't it? So one's lagging behind, one draws it all in quickly, okay, what they're going to do when you put them both in the same circuit?
Cancel each other out.
Cancel each other out. Okay, so that's what we've got here. Is we start off with the XL being up high. Now we've got this capacitor in. It's going to end up correcting it down. Okay, because it starts to cancel each other out, which is why I said it stays in the positive realm, because they're cancelling each other out. Okay, and that's how we end up with this peak line being XL minus XC, and we end up with our Z being there now. Okay? By putting in the capacitor on an inductive load, it helps us to correct the power to bring it all into unity. Okay? Does that make sense? Fantastic. Okay? Any questions on what we've covered so far?
What you just said, where you put them both together and they cancel each other out, is that to create a magnetic field, or is that to draw in loads of current?
So what it's for is, if you think about the pint glass I talked about last week.
Yep.
I did talk about pint glass analogy last week, didn't I?
Yeah.
Cool, because I've done this same lesson like 3 times now. So when you think about the pint glass, think about the resistance being the liquid when we look at it as resistance. Think about the wasted energy being this sort of side, where it's not actually doing anything. It's a waste. Okay, that wasted power, the reaction of putting the AC current through the inductive load, okay, creates a higher resistance in the circuit, doesn't it? Which isn't doing anything for us. So if you think about the head of a pint, you want to try and reduce that down to reduce the wasted energy that isn't physically doing anything for us. Okay, who likes to drink a fizzy drink with a large head? Loads of froth. Right? Anyone like to drink the froth from Fizzy Coke? Right? No one does. Right? Imagine having to pay for a whole glass of just a froth. Okay? It's wasted money, isn't it? Froth. You know the fizzy bit? Okay.
Obviously,
What?
it's wrong, so I'm going to waste it.
Was that after the large head?
No. That's a good one. You're sick in the
Not the first
You've
time
got
I've
to be
been
here
told
to be
that.
studying this late at night, haven't you? Okay. So the reality is we put a capacitor in to do power factor correction. So one of the things that we're going to be looking at next is power factor correction, because we want to get as much energy out of this doing work for us rather than being wasted. Okay. So when we've installed fluorescent light fittings, they're an inductive load, aren't they? They've got a ballast, or some people call it a choke. That's an inductive load that uses energy but also wastes energy at the same time. Okay, because of the coil of wire. So they've always got a capacitor installed on the terminals to correct the power factor, to make it more energy efficient. That's why they are so energy efficient, because they self-correct, because they've got a capacitor installed already. Does that make sense? Fantastic. Okay. So talking of that, we're now going to start looking at this whole theory in the realms of power. Okay. So, power is energy. Okay. It's a period of time measured in watts, and it's represented by the letter P. Okay. The one thing that this PowerPoint's okay. So the way energy is calculated is Q divided by times by V divided by time. Okay. Q is coulombs. Coulombs is the measurement of electrons. Okay. And it's the electrons that are moving times by the voltage, which is the force moving them along, isn't it? Divided by time. We can simplify this formula to what you're more likely going to use in real life is voltage divided by current. Because current is the Q divided by T equals current. Okay? I don't know why they like to throw that one in at level 3, because that's that first one. Okay? This formula will only work in a DC circuit. Okay? Right? This only applies to a DC circuit because when we work in AC, we end up with a power factor now, don't we? The voltage and current aren't constant. We end up with an inductive load having a leading power factor or a lagging power factor, depending on what's being applied to it. So it's going to end up causing this formula not to actually work for us for what we want to do. Okay? So, we have a new triangle. Okay? One thing to notice, the one thing that I haven't rubbed off this triangle is the power factor of cosine. Okay? You can calculate power factor using the resistance triangle. You can also calculate it with using this triangle as well. You should in theory get the same value. Okay? That's the theory behind it, don't quote me on it. Okay? By the end of the pentagon. Alright, so on our new triangle we've got true power. We've got the true power, we've got the apparent power, and we've got our reactive power. And just to link this back to what I've talked about before, okay, there's my dodgy mug. Okay, that's my apparent pint, isn't it? Okay,
Left-handed cup as well.
Is that more your style? Little baby beaker. Okay.
Give him a stroke. Yeah, look, it was an animal.
What was it? Wednesday. Yesterday I was teaching this to the full-time level 3, and one of them went, before I even said anything, he went, "It's a mug." And my first response was, "Well, it's like looking in a mirror then, isn't it?" I was very harsh to them yesterday. I don't know what was wrong with me. It was very quick. So this is our apparent pint. So we can relate this to being this volume here, can't we? Okay. Who knows? You'll know this anyway. The Pythagoras theorem, when we look at the squared numbers, it's about the fact that if you were to draw this as a square and this as a square, those two volumes will fit into the same square that you draw off of there. Okay, did you all know that? No? Okay. So that's the idea behind Pythagoras' theorem. That's why we square the numbers. So we get the volume of that square. Okay? And those two squares fit perfectly into my dodgy ass square because there's not enough space for me to draw a square there. Okay? That's why I go for a pint glass. Because it's a volume, isn't it? Yeah. Okay? So in that volume, I'm going to have my true power. Okay? My true power is going to be my liquid. That is the power in the circuit actually doing work. Okay? That's measured in kilowatts. Okay? We then have the reaction. So if you think about it with pouring a drink of Coke into a glass, what ends up happening is you pour that drink into a glass.
Fizzes up.
It fizzes up, you get the froth, you get the head. Right? Not the throbbing head though, okay?
No, that comes after 10 points.
Okay, so we call that our reactive pint. That's the reaction of taking the glass and pouring that drink into it. Okay? So you've got to think of it, it's the same as when we put the energy into the circuit, we have our inductive load, we have our capacitor. They both use power, don't they? Okay? But it's not power that's going to really do anything for us. It's power that's wasted. Okay? So when we have an inductive load, what do we put in there to try and reduce that wasted power?
Capacitor.
A capacitor, because it does the opposite. So on an inductive circuit, we put a capacitor in there to reduce that head. How do we reduce that froth when we pour our drink at home? Tilt the glass. Okay? By tilting the glass, it allows you to fill it up and not create as much fizz on top. The other trick you can do as well is if there's a little bit of water in there, that helps to kill off the fizz as well. Okay? Or stick your finger in it. Depends what you've been doing with your finger though. You dirty-minded kids.
What was that in the throbbing head?
Okay?
God, never got this in Heaven's class.
So we've got a few things that we can be able to work out from this. Okay? So, we have here the apparent power. Okay? The formula for working out apparent power is actually in the unit titles. Okay? It's measured in kVA. So if I took just the VA, what was that someone saying? Say it a bit louder. It looks like voltage times by amps, doesn't it? Okay? That is how we calculate this. And to get it in kVA, we do voltage times by amps divided by 1,000. Let me write that again. Okay? Does that make sense so far? That's a really simple one to work out for, isn't it? So now we look at our true power. True power is measured in kilowatts.